Okay, we're going to go ahead and get started again with our last talk of this morning breakout session, which will be Saloni, Sinha. We're going to talk about the Riemann hypothesis via the generalized von Mangoldt function.
Okay, thank you for the introduction, and I thank the organizers for giving me the opportunity to speak today. I am going to talk about the Riemann hypothesis via the generalized von Mangoldt function. And being the only grad student in my department doing number theory, I have the habit of making my talks super accessible. So it should be like pretty easy to follow. Okay, so we're going to start with at the beginning of time with the Riemann zeta function. So let S be equal to sigma plus IT, that it's a complex variable. And the Riemann zeta function is defined as the series n going from 1 to infinity, 1 over n to the s. And it also has this Euler product form, which is the product over all primes. So whenever you see a p here, that's going to be a prime number. And the Euler product form is 1 minus p to the minus s to the power -1. And the Riemann hypothesis asserts that all non-trivial zeros of this zeta function, they lie on the real part of s equal to 1/2, right? And we also call it the critical line. And if we take the logarithmic derivative of the zeta function, it's related to the von Mangoldt function. So minus zeta prime over zeta is equal to this series. So basically the Dirichlet series corresponding to the von Mangoldt function. And the von Mangoldt function is defined as log p if n, so lambda of n is log p if n is a prime power and it's 0 otherwise. Okay, so our result is based on this result proved by Gonick, Graham, and Lee in 2020. And their result, a formulation, this is sort of like an intermediate result in their paper. But basically what they say is that a necessary and sufficient condition for the truth of Riemann hypothesis is that if you have any fixed constants, epsilon and b bigger than 0, then we have this uniform estimate for the twisted partial sum of the von Mangoldt function. So by twist, I mean this n to the minus iy term. So it basically, like you just sort of rotate on a circle. This partial sum, this is equal to x to the 1 minus iy over 1 minus iy, plus you have this error term of x to the 1/2 times absolute value of y to the power epsilon. This holds for x between 2 and absolute value of y to the power b. And of course, lambda is the von Mangoldt function. So a little bit about the result. What they do in their paper is they prove or they conjecture a generalized Lindelof hypothesis for integer sequence, and they define this to be LH of n, where n is the integer sequence. And they start off by taking this integer sequence to just be the sequence of primes. And so in their version, what they prove is that LHP, the Lindelof hypothesis for primes, is equivalent to the Riemann hypothesis. That's also sort of the title of their paper. And of course, this is like not the only sort of estimate in this direction. In 1901, Wong-Kok showed that under Riemann hypothesis, for x bigger than equal to 2, psi of x, which is the Chebyshev function, just the partial sum of the von Mangoldt function, is x plus big O of x to the 1/2 times log x squared. And actually, like with their version of what they showed, it is hard to recover that result because like y, it's kind of restricted in a sense, right? Because like your y cannot be 0. Like you have like some dependence between x and y in some sense. Okay, so I'm going to take a little bit of detour. So I'm just going to introduce two new functions, which is kind of what I work with in this result. So the first one is the k-fold convolution, which is basically just the k convolution, or like the Dirichlet convolution, the Dirichlet multiplication, whatever you want to call it. So k copies of that, and the Dirichlet series corresponding to this is just basically whatever Dirichlet series you have for the von Mangoldt function raised to the power k. And the second function I want to introduce, the second arithmetic function I want to introduce is the generalized von Mangoldt function, which is defined as the convolution of the Mobius function and L to the power k, where L is the natural log function. And the Dirichlet series, it's not too hard to compute. The Dirichlet series corresponding to this is -1 to the k, the kth derivative of zeta over zeta. Okay, so what we do in this result or in this paper is we study twisted sums corresponding to these two arithmetic functions. So you can see that it's kind of similar to the sums that was studied by Gonick, Graham, and Lee. We have the twist involved. And our goal is to reformulate the Riemann hypothesis in terms of asymptotic estimates for, again, these twisted sums. And basically, we prove the analogs of Gonick, Graham, and Lee's result with twisted partial sums involving, so I'm going to call it lambda power k, which means the k-fold convolution, and lambda sub k, which is the generalized von Mangoldt function. Okay, so building up to the actual statement of the result. So yeah, my advisor was like, make sure your audience understands what the result is. So psi power k, so that's basically the Dirichlet series, or that's basically the partial sum in associated with lambda power k. So what we have, the first theorem is if the Riemann hypothesis is true, k is any natural number, then this is the sort of form that we get for the partial sum. So the partial sum is right here. So we have like this main term, which is associated with the Dirichlet series corresponding to lambda power k. So you get some sort of residue here, and then you get an error term of x to the 1/2 log x plus absolute value of y to the power 2k plus 1. And this holds uniformly for all x, y, and r. So it's not restricted in that sense. X is bigger than equal to 2. The implied constants, they only depend on k. And the residual term, so a couple of caveats here. The residual term can be eliminated if absolute value of y is bigger than square root of x, and the exponent 2k plus 1. In case k is equal to 1, we don't actually have 2k plus 1, we just get 2. And then in the reverse direction, so this is like a strong converse of the theorem. So basically, what we say is that if for any epsilon bigger than 0, this estimate holds. So this is not the same estimates. I don't know if you noticed, but the error term here is x to the 1/2. We are not using log here, in some sense using like a stronger estimate. So we have x plus absolute value of y to the power epsilon. If this holds uniformly for x, y, and r, x bigger than equal to 2, then the implied constant, and where the implied constant only depends on k and epsilon, then the Riemann hypothesis is true. So this is like, for lambda power k, we have basically similar statements for lambda sub k. So before I get into that, just want to point out a couple of applications of this. So with k equals 1, this is what we get, right? And this is kind of similar to Gonick, Graham, and Lee's result, but it's a little bit stronger in some sense with, like x and y sort of not being very restricted. And with k equals 1 and y equals 0, we are actually able to recover the result of von Koch, which I showed before. So like if you just plug in k equals 1, y equals 0, you would recover this result. And like just another sort of example, like if k is equal to 2, then we get this sort of like nice form. I'm going to say nice in quotes, but yeah, we get this sort of a form where you have like this main term, this error term. And yeah, it's just like a nice expression to write out. Okay, and going to the second or like the third and the fourth theorem, so like the theorems corresponding to lambda sub k, we have basically a similar statement. Here we also have like the residue is associated with the Dirichlet series for lambda sub k. So that's the kth derivative of zeta over zeta. And then you have this error term x to the 1/2 log of x plus absolute value of y to the power 2k plus 1. So basically, like same as before. And then for this also, we have a strong converse. Again, also very similar. So yeah, again, the residue term, like, the estimate that we are looking at is this one, where the residue is associated with, the Dirichlet series corresponding to lambda sub k. Okay, so with this one, we also get, like just sort of to write out this form for lambda for the generalized von Mangoldt function. So lambda sub 2. So lambda sub 2 is basically just mu star log squared. We get this sort of an estimate right here. We have this main term, this error term, and it holds uniformly for all x, y, and r, x bigger than or equal to 2. And if you, again, sort of like plug in y equals 0 under RH, this is the estimate we get. And yeah, again, it has a nice form. I didn't mention this before, but like I know the C naught was there in a few of these examples. C naught is just the Euler-Mascheroni constant. Okay, so a few implications of this result. So first of all, like it's very well studied that the distribution of primes is influenced by the zeros of the zeta function, but our results also suggest that it also exerts an influence on almost primes. And the reason being that if you have something like, lambda square, for example, then it's supported on the set of almost primes. So that's sort of how that relation works. And we also expect that these results hold for a wider class of arithmetic functions. So for example, like just taking a very naive estimate for the Mobius function, under RH, we can show that there's a constant such that the twisted partial sum associated with this Mobius function is less than x to the 1/2, and this exponential term right there. So this is taking like a very naive estimate. But of course, like, if we take like better estimates for the partial sums of Mobius function, we can get something even nicer. Okay, so gonna delve a little bit into the proof of the forward and the backward direction. So you can see the statements are really similar. So we prove theorem 1 and 3 together and 2 and 4 together. So 1 and 3 is basically the forward direction. 2 and 4 is the reverse direction. Okay. So gonna start with like some sort of like technical details here. But we let sigma naught equal to 1 plus 1 over log x, and t is almost the size of square root of x. And we use the Perron's formula to sort of establish like a relationship between partial sum and the Dirichlet series, right? So for theorem 1, like this a sub ny that you see here, that's going to be like, this term, so lambda power k and to the minus iy. And the Dirichlet series corresponding to that is, as I mentioned before, is just the kth power of minus zeta prime over zeta. And for theorem 3, so the one corresponding to the generalized von Mangoldt function, we get the term, so again, similar lambda sub k n to the minus iy, and then you have this Dirichlet series. Okay, so as you can sort of guess, like in the statement of our result, we have the residue term. So that might give a hint that we are taking some sort of a contour integral in this case. So we basically split into two cases. For k equals 1, we prove it separately. We kind of have like a better, like we shift the line of integration basically to -1 in the first case. And for the second case, so by second case, I mean for k bigger than or equal to 2, we shift the line of integration kind of close to the half line, but like we don't cross it. Right? And actually, like for k bigger than equal to 2, there are some complications presented by, like multiplicity of zeros and stuff like that. Okay, so again, just some sort of technical details, but to So basically, like to find the contour integral, we want to estimate, so the contour integral itself gives the residue term. And the idea is that the other sides of that contour, so the two horizontal lines and the one vertical line, they give you whatever they give, like it goes into the error term. And so basically what we want to do is we want to derive estimates on the Dirichlet series on like those horizontal and vertical lines. So we do this by, like basically just to get some, so to get estimates for like kth derivative of zeta over zeta, or like, zeta prime over zeta power k, we sort of use this functional equation. We get this expression using the functional equation, and we just sort of bound the terms involved here. And this is, so I'm not going to go into details, but like these are the estimates we get. And they hold throughout this region, and this region is actually like within the contour. So we are all good. Okay, and the proof of the strong converse, this is basically based on like a method developed by Pence to study like some oscillations of Mobius functions, stuff like that. But this is the method they also, like Gonick, Graham, and Lee, they also sort of use. So it's just sort of based off of that. So here, we let this capital psi xy to be the partial sum, again, sort of similar to what we were seeing before, n less than equal to x, a sub ny, where again, a sub ny could be either the term associated with lambda power k or lambda sub k. And then we let rxy, we define this to be this capital psi xy minus the residues term. So that's basically like the error term that you see. And for both theorems, our hypothesis is that this error term right here is less than x to the 1/2 times x plus absolute value of y to the power epsilon. And we want to show that if this holds, then the Riemann hypothesis is true. So what we do is we basically prove this by contradiction. So we suppose that there is a zero which has the real part. So the zero is beta naught plus I gamma naught. And we assume that this beta naught is bigger than 1/2. And we define this metamorphic function, capital H of S, which is the integral from 1 to infinity of r times x to the power minus s. And we define this another function, which is basically just some sort of a translation of h. And the only reason that we do this is to like make the calculations a little bit easier. And if m is the multiplicity of like this particular problematic zero, then we also define this new function, kappa s hat. So s hat is basically this sort of translation right here. And I know it looks like pretty random, but as you know, as most things go, like there's a reason behind all like, defining something this way. So this function, kappa s hat, it has been crafted so that it's metamorphic for s hat in C. The product has no pole in the half plane other than a simple pole at s hat equals rho naught. And that's really like sort of important for this method to work. And then some other things involving convergence of integrals, stuff like that. So basically what we do is we calculate this integral. So you can think of it as, so I didn't mention this before, but small h of s is again some sort of a translation of kappa. So we calculate this integral below in two different ways, and then we just sort of compare them. So the first way is by shifting the line of integration to sigma hat equals 1/4. So sigma is the real part of s hat. And to calculate this, like, yeah, we again sort of like make a contour, and like we get some sort of a main term here, which is c times x to the power rho naught minus iy plus 1. That's the residue of this function at s hat equals rho naught plus an error term of x to the power 5/4. And The C, if I write it out, it would actually take the whole slide. It could actually be a cool undergrad project, not gonna lie, it's pretty fun. And the second way is by changing the order of integration. So if you change the order of integration, you are basically able to conclude that this integral is less than the integral of r from 1 to x. And by our hypothesis, where r has, r is less than like the error term that we have there, this integral, this comes out to be less than x to the power 3/2 times x plus absolute value of y to the power epsilon. And then comparing the two integrals, what we end up getting is that for every epsilon bigger than 0, x to the power beta naught plus 1. So beta naught, remember, that's the real part of that problematic 0, right? This is less than, oh, sorry. This is less than, this particular term. So that was the residue from the first integral. And this is less than what we just calculated here. So this gives us a contradiction because we assumed that beta naught is bigger than 1/2, right? So you're saying that this thing is, less than x to the power 3/2 times something. So that gives us the desired contradiction. And with that, I'm going to end. Thank you so much.
Questions for Saloni?
There you go. Yes. In the other direction, we get something like this. So we're using like a different error here. Correct. It was this. Yeah. Yeah, I know it's yeah, it's kind of technical in many ways. Well, I guess like that's only because like we do, so when we do assume RH, we sort of get a better error term naturally, but like in the other direction, like we are trying to get to RH, so we kind of have to take like a better error term itself, yeah. Yep. Yes. Yeah, it's on archive. Yeah. Yeah, for those of you interested in the more nitty-gritty of this, yeah, feel free to check that out.
Okay, do we have any other questions or? So then I think let's thank Saloni again.